Hi, so this is a video editorial for the LeetCode Biweekly Contest 182. The contest was like decent. It was on the like the middle end of difficulty in my opinion. Like I should have solved this faster, but like my implementations are very weak. So like as always, I'll be going through the explanations for my implementation of the problems in the order of the appearance of the problems, and then after my explanations, I'll also attach a live solve section where you can see how I approach the problems in the live contest scenario. All right, so Q1 was like basically a straightforward implementation problem. You had to do what the problem just said. Basically, we had a score and a counter, and we were given an events which were like strings. And based on some like input, we had to do the output. So if the input were any of these, we add that to the score. If it were W, we increase the counter by one, and else for both W, D, and NB, we add one to the total score, and at the either all when all events have been processed or when the counter becomes 10, we return this array. So yeah, you just do this is the score comma counter. If the size is 1, then it's one of these, right? So in that case, if it's W, then we result do the counter plus plus, else we make it an integer and add that to the thing. Else anyways, it's one of these, so we add that to the score. At the end, if the counter gets 10, we break and we return. So yeah, this was Q2. Q3 was an interesting problem. Basically, you are given a string which should not contain, you are given a binary string S which should not contain either this or this as a subsequence, not a substring, as a subsequence, right? And in one operation, we can perform the following operation where we either flip 0 to 1 or 1 to 0, and we have to find the minimum number of flips to make S a valid string. So yeah, this was the problem statement, and the constraints were n is less than the length of the string n is less than equal to 10 power 5, and obviously the characters are either 0 or 1. So my implementation for this problem is slightly different. Initially, I was thinking like, because of this pattern, what we have is basically, if we have a 0, there should not be any two ones in front of it, right? So either we make the two ones 0, or we make the there shouldn't be like two ones to the right of it. So either if there are only two ones, we can make one of them 1 0, but if there are multiple ones, we'll have to do this. And similar thing you can do on its behind direction as well. But I was thinking about doing this, but then I was like, okay, I have a DP formulation as well. Basically, this was my DP idea. I0 is the index I am on this string. I1 is the index I am on this string, and I is the index I am on the actual string, right? So if this or this string has been completely taken in my input string, then that means this exists in the input string as a subsequence. So I'll return a very large value, so it deflects the answer. Else I'll return 0. Or the main thing is either I'm not flipping anything. If I'm not flipping anything, then I'm considering the actual value. Else if I'm doing a flip, I'm considering this. So basically, if it's 0, I'll take this as 1, and if this is 1, this becomes 0. And based on that, I'm moving these two pointers ahead, and obviously I will always become I plus 1, and at the end, we want the minimum operations, right? Here we are adding 1 because we are flipping it, and we are considering the yth character here, cy instead of cx, which is the actual character. So this was a easy implementation. That's why I went with the DB direction. Since n is less than equal to 25, and we have like it's a constant size DP, so this will be 9 into n, which works fairly fast, I think. I mean, not that fast, but yeah, still it works. Q2 was an interesting problem as well. Basically, we are given 3D points, x comma y comma z, and of n 3D points and a target, and we have to find the number of iterations basically such that target exists in our this points array. And the operation we do in every iteration is we select every distinct pair and we merge them like this, basically x1 x2 by 2, y1 y2 by 2, and z1 z2 by 2. Now the main thing with this problem were the constraints. We have this n is less than equal to 20, and the more important constraint is this x1 y1 z xi yi and zi are less than equal to 6, 0 to 6. So why am I saying that the other constraint is important? Basically, if we have this if we have this, right, xi comma yi comma zi, we have this, right, and these values all have to be between 0 to 6, which means if we consider all of these values, this can take 7 places, like 0 to 6, this can take 7 places, this can take 7 places, right? So in total we have 7 power 3 distinct values possible, since the points have to be distinct, right, in our operation anyways. Yeah, we can't do anything with duplicate points. So in total there are only 7 power 3 distinct values, and because n is also less than equal to 20, and 7 power 3 is what, 343, I think, if I recall what I'm doing once again. Yeah, 343. So at max, our size of our total array becomes a 343, right? So basically, we can just do a brute force where we take the input, we perform the iteration on every pair, which is at max, it will become 343 square. Like this is also a very high upper bound. It will become 343 square, and in that, basically, we can see after performing, if we found the thing in our, if we found the target, we'll be like, okay, return the number of iterations till now, else we repeat. And if we have reached the cap, then we stop. So this was my implementation. And another important note is, instead of putting this vector like of x comma y comma z in our points array, since the points are fairly small, it's there from 0 to 6, what I did was I encoded the points in integer. Like, so if we have some, let's say, point 3 comma 0 comma 7, not 7, 7 is not possible, 3 comma 0 comma 5, I made this like 305. So basically this is the hundredths power, this is the tenths power, and this is the ones power, right? So this will make the implementation even faster, because I was still having slight doubts, right? So yeah, this is the thing. Basically, this is the encode function, which takes a vector and encodes it into the number. This is for performing an operation. This is very ugly, I know, but still. This is for performing the L1 and 2 L3 operation. This is for getting the digits from the number. This is basically decoding. This, I told you my implementation was really off. Like, there's obviously a better way to do this, but yeah, regardless, this is this thing. We are doing this operation, right? X1 plus x2 by 2, y1 plus y2 by 2, and z1 plus z2 by 2. So this is the left number and right number. We are doing this, and again making it a number and returning. This I just made to make my implementation even easier. So I first encode the target, and I make another vector for my points, which is the encoded points. I make them unique. Unique is basically this. You could have used, you can use a set as here as well, but I wanted to like make sure my runtime isn't that high. First of all, I'm fine. If that exists, then the number of iterations till now is fine, right? So we return k. Else, like for every element in the original size, we push them into this new vector. And then for this new vector also, we make the operation where we do the uniquing. And if there are no changes, that means we have reached a limit of 343, right? In that case, we break and we return -1. Else, we update the input vector. So this was Q3. And in Q4 as well, my implementation was really weird, but it is what it is. We are given a graph. With obviously n nodes, 0 to n minus 1, and edges which have like bidirectional edges, u comma v, with the weight w. What we have, and we are also given source, target, and k. And what we basically have to do is we have to find the minimum threshold such that at least one path exists from source to target, right? And since it is bidirectional, like it could be target to source as well, but that doesn't matter. And now the main condition is edge is light if the weight is less than equal to the threshold, the chosen threshold, and if edge is heavy if it's greater than threshold, right? And at most we can have only k heavy edges. And the constraints were very weird for this problem for some reason. The n and m are less than equal to 10 power 3 for some reason. Like my solution will work with 10 power 5. Like my solution works for n comma m less than equal to 10 power 5. I have no idea why this was 10 power 3 here, but anyways. So yeah, what was my intuition? Like, because of these constraints, first of all, I was like thinking in some sort of DP thing, but I was like, okay, this is clearly a bait. My idea was this threshold is obviously monotonic, right? Because like if the one second, if some threshold x can be true, then obviously x plus 5 is also true, because like this will have the same number of less than equal to, this will have less than equal to heavy edges than this, right? So, and we have the utmost condition on k. So obviously this is monotonic, so maybe we can binary search on the thing, which is what I did. My implementation was this only. What I did was, and I'll let you know of a better implementation after this, but basically what I did was I assumed some threshold, some like limit or some x, right? Let x be the current threshold. Now if an edge is light, that means less than equal to threshold, we can always take it. Like it won't contribute to the k anyways, so we can just take it. So what I did was, for every let's say we have some graph here. For every edge which is less than equal to threshold, I connected them regardless if they are important or not, right? So like these are all light edges, right? And now we have some heavy edges remaining. There will be some heavy edges remaining, obviously. And these will all contribute 1 to the k value. So now what I did was, we have some separate components, like we have this, we have this, we have this, and we have this. We have all these components which are separated by heavy edges. So now what I did was I condensed this into a separate graph. So we have just this graph of different nodes which are connected by heavy edges. 1 second. Yeah, we have this graph, and on this graph I did a BFS from the source component, the component which has the source node, to the component which has the target node. And if I traverse over, BFS will obviously find the shortest path, right? And if I traverse over more than k, like if the distance which is measured in now heavy edges, since we are since the only the heavy edges are remaining now, if that distance is greater than k, then that means this threshold we chose was too small, and this binary search will go back. So this was my implementation. I'll go through the code. Obviously DSU, this is the binary search thing. If it's valid, then that means we can minimize, else maximize. Obviously sometimes it can be like Rmax as well, like if they are in different components only, like if they're not connected anyways, then the answer won't be valid. So like this is just for that. In my is valid, this is, I'm just clearing the graph because I'm using the same graph here, right? So this is my clearing and resetting the DSU. For every edge which is less than equal to the weight, I'm just unioning them, like connecting them in the DSU regardless. And if in doing that my source and target become connected, then obviously I can go right. If they're in the same component only, then there's no need for the heaviest traversal. It will always be less than equal to 0, so I can return true. Else I'm doing this. If the weight is greater than limit, then I'm doing this DSU thing where I'm connecting the parents. I'm only connecting the parents of every component in the graph. And then I'm doing this BFS. And in the BFS, I'm getting the parent of the source and parent of the target. And then this is a traditional BFS thing. At the end, I'm returning the distance. So this was my implementation. And even better implementation is we can just do 0 and BFS on this. If the weight of the edge is less than equal to the threshold, then you can consider this as a 0 edge in the 0 and BFS. Else this is a 1 edge. The threshold will be binary searched, and this way you won't have to make this. You won't have to use a DSU at all. Just we can use the original graph. We won't have to make multiple graphs here again and again as well. So that approach will be even faster. All right. So this was my implementation and my solutions. Let me know if you have any doubts regarding this or anything else. And yeah, you can watch me solve this, see these problems in my, you can watch my live solve attempt at these problems and see how I struggled. Like, all right, bye.